Okay, well, I've got 10 o'clock on my clock, so I'm going to go ahead and start it. Maybe some people are getting ready to log in and just haven't gotten there yet. Or maybe they went to the old ID meeting and they're sitting there going, what's going on? Everybody get their tests back, okay? I sent those out as an email as an attachment, so I'm hoping everybody got their tests. Okay, so I'm going to assume that's true. You want to hang on to those old tests and quizzes because we will be, hi Peyton, we will be using those, you can use those is what I'm trying to say for the final exam because it is a comprehensive final. So it'd be a good idea to hang on to those and you can use those to study from. Also, I just wanted to, I think I've got everybody set up now in terms of where they're going to be taking the test next week. So if you're doing things at a regional campus, I'll be sending those tests to the administrators there at those campuses so that they can have those handy when you show up. And if you're coming here, then remember that's going to be in Johnson Hall 221. So that's kind of where we're going. It looks like Peyton's walking down a hallway. Sorry. It's just kind of, I kept looking at it. It looks like we're going down a long tunnel. All right. My bad. I'm going to make sure I get Brittany down. All right. So what I want to do today is, first of all, the quiz is open that you're taking this weekend. I don't know if you've gone out there to look, but has anybody tried to go ahead and download the quiz? And it's okay this time. I know last time I thought I had it set to go and then for some reason it wasn't showing. And so I think I had everything, all the right buttons set in Moodle this time. So, all right. So were there any leftover questions then from the number-based stuff that you want to ask about? You know, basically on that quiz, what you're going to be doing is counting in a base, doing addition and multiplication charts in that base, converting some numbers back and forth from base 10 to that base, and then doing some addition, subtraction, and multiplication in that base. So the idea was to just see if you could operate and do the basic kinds of things in a base other than base 10. So if that makes sense to you, then you should be in good shape with the quiz.
And which chapters was this over?
The quiz is just over 3.5. It's just that, because that's kind of the new stuff, the harder stuff. 3.4 is kind of hard sometimes to quiz over estimation and rounding and things. I mean, you can, but I figured we'd just stick with sort of that process of how to teach that general sequence, but do it in base. I think the quiz is base 4 instead of base 10. So if you can do things in base 4, then you should be good to go. All right, then I'm going to go ahead, if you guys feel pretty good about that section, and talk about some of the stuff in Chapter 4 that you're going to be looking at. So the majority of the test next Friday, or whenever you're taking it, some of you are taking it on Thursday and Wednesday, whatever, but it's going to be over 3.4, 3.5, and then 4.1, 4.2, 4.3. You might see a couple things from the last test, the Chapter 2 test. So you might want to go back and kind of look at the test that I just returned and, check that out again just before you take the one. Now, some reminders, when you take the proctored exams, you're not going to be able to use any notes. You're not going to be able to use a calculator. So I write the test with that in mind. I write it knowing that you won't have access to other materials. That just, I don't want anybody to come in and be shocked because you can't use notes or you can't use your calculator. I know you can do that, obviously, when you're taking the unproctored tests. Okay, I'm going to switch over to the document camera. So let me do a share screen here then. And I want to talk a little bit about this material in Chapter 4 that we're going to look at. The material in Chapter 4 is really kind of getting you ready to make this transition from what we do in K through 4 into what kind of happens in 5th grade and through middle school. In the old sequence of classes that we used to have, pretty much what we've done these first 4 weeks is what we used to call the 118 class. And it was, like I said, focused on the whole number math that we do in those earlier grades. And then the old course sequence, we had 318 came next. which was that more middle school math where we did integers, fractions, decimals, percents, ratios, proportions. And so that's kind of what we're going to focus on the second half of the semester after next week and the midterm test. We're kind of transitioning into that content from the other course. So chapter 4 is sort of the content that connects those two together. It's what we call number theory. And it's basically got some things in it that are skills that are necessary to make that transition from thinking about all of our numbers and operations in terms of just whole numbers and just based on counting, because really that's what whole numbers are based on, is the act of counting. But it turns out that there are some things that math needs to do, namely measure things that you can't do by counting. You know, if you're measuring a table, or you're weighing something, or you're driving down the road and want to know, what the speed limit is, those kinds of things, those don't generally come out to be, exactly whole numbers if you're measuring precisely. And so then we have to have different types of numbers, and that's what number theory does. It allows us to make that transition. So there's kind of some definitions that we need to start off with. When we look at numbers, we want to talk about sort of the difference between prime numbers and what are known as composite numbers. Somebody think they've got a good definition for prime numbers that they would want to share with us? Hang on a second, I need to turn on a screen. I should have done that before class started. Okay, somebody came into the room, so I needed to be able to let them see what was going on in the class. I hope that's coming on. All right, nobody's brave enough to tell me what their definition of prime numbers is? Tyson, I'm going to volunteer you. What do you use as a definition for prime numbers? Oh, Tyson go somewhere? I don't see him on there anymore. Maybe he had to step away.
Find the answer.
Okay, did somebody say, I heard something, but I couldn't actually make out what you said.
Sorry, I don't mind the answer. This is Lindsay.
Oh, okay.
Are numbers that can only be multiplied by one within themselves.
Okay, yeah, basically prime numbers are, and I'm going to rephrase what you said in a way that I think is a little more exact. Prime numbers are numbers with exactly two different factors. One and the number itself. Now, the reason I kind of put that extra wording in there, exactly two different factors, was because I wanted to eliminate the number one from the set of prime numbers. One is that special identity number for multiplication. So when you multiply anything by one, you get that other number back. So we don't consider one a prime number because it's a factor of everything, basically. So by saying we have to have exactly two different factors, that means that we can't use 1 times 1 equals 1 to justify that being a prime number. So what is the first prime number? Or the smallest prime number, I guess I should say.
2.
2. And that is the only even prime number, because every other even number after 2 is divisible by 2 as well as 1 in itself. So we know it has more than two different factors. All of the other prime numbers are odd. So we'd have 2, 3, 5, 7, not 9 though, because 9's got 3 as a factor. 11, 13, not 15 because it's got 3 and 5 as factors. 17, 19, 23, 29. How many prime numbers are there? That's a good question, yeah. And it's a question that was actually answered by the Greeks about 500 BC, if you can believe that. It's something that we've known for a long, long time. Turns out there are an infinite number. I'm going to put a dot, dot, dot here. There's an infinite number of primes. And ancient Greek mathematicians proved that back 2,000, 3,000 years ago. So that's something that we've known all along. Now, composite numbers then, if we kind of take this prime number definition and change it slightly, prime numbers are numbers that have more than two unique factors or two different factors. So these are numbers with more than two different factors. All right, so pretty much if you're looking at the set of if you're looking at the set of natural numbers or counting numbers or positive whole numbers or however you want to think about that, numbers fall into one of those two categories. You've got the number 1, which is an identity, so we're going to take it off the table. But if you go from the numbers 2 on, they're either prime numbers or they're composite numbers. And they can't be both. You're either one or the other. So those are disjoint sets, as we like to say. Now, I want to make sure that everybody's clear on the difference between factors and multiples, because I'm using this term factors. And remember, factors was what we call the things that you multiply together. But in a general sense, when we're looking at it just as a term itself, factors mean we'll say given n, factors of n are the natural numbers that evenly divide n. So in other words, if I wanted to know if 2 was a factor of 21, I would take 21 and divide it by 2. That doesn't go in there evenly. Dividing evenly means there's no remainder, that it goes in a natural number of times. So, for instance, sometimes you'll see this notation. If I want to know what are all of the factors of 12, then I'm saying, what are all the different numbers that will evenly divide 12? Well, we know that 1 goes into every number evenly. 12 is even, so we know that 2 goes in there. It's also divisible by 3 and 4 and 6 and 12. So the factors of 12 would be this set of numbers. And notice that this is a finite set. You can count how many factors 12 has. It has 1, 2, 3, 4, 5, 6 factors. All right. Also notice that they sort of come in pairs. I always like to list my factors in order from smallest to largest so that everybody's list sort of looks the same. But you can also notice that if I take 1 times 2, there's my factor pair to get 12 as the product. So 1 times 12, 2 times 6, and 3 times 4. So that's something that, you know, as you're looking at your list, make sure that all of the factors in your list have a partner, unless it's a square number. Like if you were doing all the factors of 9, then in that case, you're going to have 1 and 3 and 9. And notice that 3 is basically its own partner, because if you take 3 and square it, you get 9. So when you have square numbers, you have an odd number of factors. When you have non-square numbers, you have an even number of factors. So that's kind of another sort of number theory thing that you get into when you're looking at lists of factors. All right. Some of you, I think, when we did the first quiz, confused factors with multiples. I asked you for a list of multiples of 2 or 3 or something like that on the quiz, and you gave me a list of the factors. Okay, so you were giving me this list, but I wanted the list of multiples. And multiples are sort of the flip side of factors. These are, so we'll say multiples given n, multiples of n would be 1 times n, 2 times n, 3 times n, 4 times n, and so on. And multiples then become an infinite list. So if I wanted the multiples of 12, then my list would have 1 times 12, 2 times 12, 3 times 12, 4 times 12, and that list just goes on and on and on. So when we're talking about multiples, that's going the other direction from factors. Here we want things that will evenly divide n. Here we want numbers that n will evenly divide. So we're kind of turning it around. All right. Now, one of the things that sometimes we have to do when we're dealing with numbers is come up with what we call the prime factorization of a number. And a prime factorization is basically a renaming of the number as a product of all of its prime factors. So this would be a product of primes that equal a specific product. So let's say that I wanted to find out what the prime factorization of 36 was. Is everybody okay with this? Can I take this top one off? Anybody still copying that? And again, I'll make these notes available, so if you've missed something, you can go back and fill in the blanks later. Okay, so if I wanted to come up with a prime factorization of 36, that's probably a small enough number that most of you could do that in your head. But let's say that we don't know how to do that in our heads. There's 2 main methods that we use to do prime factorizations. There's what's known as a factor tree, and then there's what I call continued division. And I don't really care which method you use. I wanted you to be aware of both of them. Factor trees are pretty common for a lot of people to use, and you basically, as long as you know any 2 facts that will multiply together to give you 36. For different kids, that's going to be a different pair of numbers. Now, 1 times 36 is not going to help you. You want something that has at least one, the numbers need to be different than 1 times 36 is what I'm trying to say. Otherwise, you don't break anything down. So I'm going to start with the fact that I know that in my nines, when I learned all of my multiples of 9, that 4 times 9 was one of the pairs of numbers that gave me 36. And I look at those and I say, okay, are either one of those prime? Well, no. So I'm going to break down the 4. 4 is 2 times 2, and 9 is 3 times 3. So now it turns out that I've got all primes here on the end, and as I get these primes, I tell my students to circle those so you don't lose one. Sometimes your tree, depending on what pair of factors you get, will get sort of unbalanced, and it's really easy to lose a little factor. If there's a lot of factors in the factorization, you'll lose them in that tree somewhere. So it's a good idea to circle them as soon as you find them. So we would say that the prime factorization for 36 would be 2 times 2 times 3 times 3. That's if we wrote it all out expanded. A lot of times, though, we'll go ahead and use our exponential notation to shorten this up. So we'll say we have 2 factors of 2 and 2 factors of 3. So 2 to the second and times 3 to the second. Continued division is just another way of thinking about this. So with this, I'm going to turn my division symbol upside down underneath the 36. And I start with the smallest of the primes, which in this case is a 2. And since 36 is an even number, that makes sense. So I'm going to say, all right, well, what happens if I take 36 and divide it by 2? Well, I get 18. Can I divide that some more by another prime? Yes. It's still even, so I'm going to divide by 2 again. So 2 into 18 goes 9 times. Is that a number that's prime? No. So what would be maybe the next prime I could try? Well, I'm going to try 3. 3 goes into 9 3 times. And as soon as I get a prime number as my quotient here, I'm done. So notice you'll see you still get 2 times 2 times 3 times 3 when you do this process. So either one that you teach your students is fine. I think factor trees have been very popular, but sometimes there's a good reason to to want your students to think of this as division. So that's a way to do it as well. One other thing I want to show you about this, if you wanted to know how many factors, so if I now wanted to know what are the factors of 36, I can actually use this list of primes to do that. So first of all, I would take each of the different primes once. So I'm going to make my list of factors. Now we know 1 is always a factor, and then 2, and then 3. All right, so you've got those. Now we want to start looking at combinations of the primes. I've noticed that if I take 2 times 2, that would be 4. So like 4 times 3 times 3 would also be 36. So that means 4 gets added to the list. And then if I took 1 of the 2's times 1 of the 3's, that's going to give me 6. All right. Now if I do this 2 times that 3, that's also give me 6. That's not a different factor because I'm looking for the different factors. But now if I take the 3 times the 3, I'll get a 9. And then let's say we take 1 of the 2's with the 2 3's. So that's going to give me, whoops, wait a minute. I want to go backwards. I'm trying to get these in order. So if I take all of the 2's and 1 of the 3's, okay? So 2 times 2 is 4, times 3 more gives me, or times 3, yeah, it gives me 12. And then now if I take all of the 3's and just 1 of the 2's, that'll give me 18. And then finally, if I take all of the factors, I get 36. Now let's make sure I got them all. So 1 goes with 36, 2 goes with 18, 3 goes with 12, 4 goes with 9, and 6 goes with itself since 36 is a square number. So I think some of the problems in your MyLabs Plus want you to take that prime factorization and come up with a list of the factors. Another way that you know how many factors you should have in your list, this is a little theorem that says if I want to know how many factors are in 36, I take this prime factorization, but what I do is I take the exponents that are here. So these are both squared. So what that means is I take the first exponent, which is 2, and I add 1 to that. And then I take the second exponent, which is also 2, I add 1 to that. And then I multiply those 2 together. So here I've got 3, here I've got 3, and that equals 9. So there should be 9 things in my list. Let's see if I got 9 things. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I've got all of them. So this is just a little way to sort of check to see if you got all the factors in your factor list. And again, you take the exponents, add 1 to each one of the exponents that you get, multiply those together, and then that tells you how many factors should be in your list. All right, that was a pretty simple one. Let's do one more example that's maybe got a little harder number to work with. So let's say that I want the prime factorization for, let's do 288. Okay, so most of us probably can't come up with the prime factorization for 288 in our heads. We might have been able to do 36 if we just thought about it a minute, but 288's probably got enough going on that's a little harder. All right, so I'm going to go ahead and use my factor tree to come up with my factorization. Now, right off the bat, I may have a hard time figuring out where to start my factor tree. That's a big enough number that a number pair doesn't just automatically hit my head. So we're going to talk here in a minute about something called divisibility tests. And the easiest of the divisibility tests is to see if a number is divisible by 2. And we do that by looking at this ones digit. Since this 1 digit is an even number, or another way to say that it's 0, 2, 4, 6, or 8, then we know that it's divisible by 2. I'll show you another one. If the last 2 digits of the number form a number that's divisible by 4, then the whole number is divisible by 4. So 88 is divisible by 4, so you could use 4 times something. It doesn't really matter though, so I'm going to go ahead and do 2, since most of you, if you looked at that, you'd probably start with 2 since you wouldn't necessarily look at that and come up with something else. So now I have to divide 288 by 2. I can do something called short division to do this. I notice that 2 will go into 2 1 time, 2 will go into 4 4 times, 2 goes into 8 4 times. So that's a simple enough problem. I could actually just kind of do that in my head in a way. All right, I'm going to circle that 2 so it doesn't get lost because that's a prime number. And now I've got 144. Now some of us know that 12 times 12 is 144, but if you didn't know that and all you could really think about was it's still even, let's go ahead and go with that route. So I'm going to do another 2. And now, again, using short division, 2 won't go into 1, but it will go into 14 7 times, and then 2 goes into 4 2 times. And so 2 times 72 will give me 144. Now, hopefully you see 72. That's a number you should recognize as one that you have a fact for. So 72 is 9 times 8. Neither one of those is prime, but 9 is 3 times 3, so I get my 2 primes from 3. And then 8 is 2 times 4. Well, I'll circle that too. And then 4 is 2 times 2. Remember I said sometimes these factor trees get lopsided? Well, here's a good example of one that's lopsided. All right, so when I come up here to write my prime factorization, again, you want to write your exponents in order from smallest to largest. So it looks like I've got 1, 2, 3, 4, 5 2s. So 1, 2, 3, 4, 5 2s, and 2 3s. Or it's maybe tidier to write this as 2 to the 5th, 3 squared. All right, so if I needed to come up with a list of all of the prime factors, or I'm sorry, of all of the factors, not the prime factors, but all of the factors of 288, then I could come over here and say, well, the exponent on the 2 here is 5, so I need to add 1 to that. And then the exponent on the 3 is 2, so I'm going to add 1 to that. And so this gives me 6 times 3. So if I wanted to make a list of all the factors of 288, there'd be 18 of them. And then again, you could use, so if I want my factors of 288, see if we can real quickly do this. I'd have, obviously 1 starts the list. And since it's even, 2 would be the next thing on the list. 3 is going to be on the list. And then 2 times 2, which is 4, is going to be on the list. And then 2 times 3, 6 would be on the list. And then 3 times 3, oh, wait a minute. 2 times 2 times 2, which is 8, is on the list. And when you do this, you might not do them in order initially. But the idea is you've got to take all the possible combinations of these primes to come up with your list. So I've got 6, I've got 8, I'll get 12 by taking 2 of the 2s and 1 of the 3s. Let's see, if I do 6, if I take 4 of the 2s, I get 16. If I do a 2 and the 2 3s, I get 18. How many have I got so far? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I've got half of them. Now, at this point, now that I've got half of the that I need, I can kind of figure out the other ones by thinking about what would be the other factor for these 9 that I have, because remember I said they come in pairs. So to kind of help yourself out, you say, well, what would I take times 18 to get the other factor? Well, let's see. To get the 18, I had to use 1 of the 2s and the 2 9s, so that means the other 4 2s would be the other factor, so that would be 2 times 2 times 2 times 2 is, oh, that's my 16. Did I miss one in there somewhere? Oh, I forgot 9. Okay, sorry, 9 goes in there, because that would be 3 times 3. All right, so 16 goes with 16 goes with 18, and then 12, well, let's see, if we cover up the factors that make 12, that gives us 8 times 3, or 24, would be its partner. And then if we do 9, that would cover up this, and that means we've got 5 2s, so that'd be 32. And then if we do 8, that would be 3 of the 2s, so that gives me 4 times 9, which is 36. And then if we did 6, that would be a 2 and a 3, so that gives me 16 times 3, which is 48. And then let's see, if we did 4, that would be covering up 2 of those, so that we get 8 times 9. 8 times 9 is 72. And then if we covered up the 3, 1 of the 3s, that's going to give us 32 times 3, which is what, 96? Check my arithmetic, but I think that's 96. And then if I cover up 1 of the 2s, that's going to give me 16 times 9. And I believe 16 times 9 is 144. And then 288. Let's see if I got them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So now I know I got them all. So there's some things in the MyLabs Plus where they want you to kind of use these prime factors to come up with a long list of possible factors for the number. All right, questions about that? Now, there's some really cool number theory activities that you can use to help your kids practice their basic skills. I know when I was in school, it was like worksheet after worksheet, you know, time test after time test, and it was really, really boring to learn the basic skills. And it turns out that if you use a little number theory, there's some really cool little number theory problems that let kids practice their basic skills, but they do it trying to solve a bigger problem that involve just basic combinations of numbers. And that's a whole lot more interesting than just what I call undirected drill. You know, if you're just drilling just to drill, that's boring. But if you're looking at different possible combinations of things to help solve another problem, that's kind of fun. And so I've got some ideas out in the notes. If you go out and look at the Unit 2 notes in the number theory, there's one that's just called number theory, I think. There's some cool ideas for games that you can play with kids or problems you can solve in number theory. Hopefully maybe next Wednesday we'll have some time to talk about those. The other thing I want to focus on today, though, is something that used to be taught actively in most classrooms, but because we have calculators now, it's kind of gone out of style to teach it directly. But the thing is, I think in terms of helping kids build really good just pencil and paper math skills, these are still really valuable skills to have, even with a calculator. And what I'm referring to are what are called divisibility tests. Now remember, I came, you know, through school during the dark ages when we didn't have calculators, so that wasn't an option when I was a kid. And so everything had to be done with pencil and paper and what was in my brain. So anything that would help me do my math a little faster, a little more efficiently was nice to know. So these divisibility tests are things where you can basically kind of look at the number that you're asked to divide into or break apart for a prime factorization or whatever, or do just a little bit of real quick mental arithmetic, and you can tell right away whether something's going to work or what's not going to work. So let me show you an example. I already talked about one of these, and that's the test for if it's divisible by 2. So if you're just looking at a number and trying to decide where to start your factor tree, then if the ones digit is 0, 2, 4, 6, or 8, the number is divisible by 2. Okay, so I can look at these two numbers. And without doing any kind of work at all, I can look at this one and say, well, I know that one's divisible by 2. I know this one isn't. Because this one ends in 6, and that's one of my even numbers in the list here. This one ends in 3, so it doesn't work. Most of us get that one right off the bat. I mean, as soon as we learn what even and odd means, we kind of get that one. So this one is yes. This one is no. So this would be the one we could actually, if we wanted to start a factor tree on that, we could start it with a 2. Well, can we get something a little more efficient than that? Well, yeah. Divisible by 4. Now, in this case, you have to look at 2 digits. So I would actually need to look at both the 8 and the 6 in this number here to see if it's divisible by 4. So divisible by 4 means the 10s and the 1s digits form a number divisible by 4. All right, so what does that mean? Well, let's look at this 12,486. Is 86 divisible by 4? Well, 86 isn't one of your multiples of 4 that you were probably forced to memorize, but it's really easy to do this in your head because I know that 4 times 10 is 40. So if I take my 86 and I subtract 40 from that, I get 46. All right, that's still bigger than 4 times 10. So let's subtract 40 again. And that leaves me with a 6. And 6 is not a number that's divisible by 4. And so because basically what I did was I took out all the multiples of 4 here by subtracting 40 until I get something small enough I can be sure of. So since 6 is not divisible by 4, 12,486 is not divisible by 4. Well, let's try a different one. What if I had 1,096? Is that divisible by 4? Well, let's take the 96 and do our little trick. So if we take 40, that takes us down to, 56, sorry. And that's still too big, so I'm going to take 56 and take 40 from that. That's going to give me 16. And 16 is one of the ones I know, because 4 times 4 is 16, so this is yes. So that means if I took 1,096, that's divisible by 4. Okay. Now, the test for 8 is to look for the last 3 digits. So the hundreds, tens, and the ones place have to form a number. That's starting to get a little less helpful. But if you happen to have a number where this hundreds digit is a 0, then it's not too bad to look at it and see if it's divisible by 8. So we're just going to write the rule, but it's not one that is necessarily quick to do. And these are supposed to be things that are quick to do in your head. So divisible by 8, the hundreds, tens, and ones digits form a number divisible by 8. So for example, if you had something like 12,008, that would be really easy to tell, because if you take the hundreds, tens, and the ones digit, you get an 8, and 8's divisible by 8, so that would work. But if I had something like 12,948, that's a little harder for me to figure out. So it's useful if you've got an easy last 3 digits to look at to tell if it's divisible by 8 or not. Okay, so those are the tests for 2 and 4 and 8. What's another divisibility test that you guys sort of already know? If you look at a number, you can tell right away that it works.
5 and 10.
Yeah, 5 and 10. Yeah. How do you know if a number's divisible by 5?
So
5, 0.
Go ahead, sorry.
Right. The ones digit is either a 5 or a 0. Exactly. So divisible by 5. The ones digit is either 0 or 5. And that's one we figure out pretty quick. If it's not taught directly, it's one that we figure out right away. We like to divide by 5. We're in base 10, so 5s and 0s are nice for us. That tends to make the arithmetic a lot easier if you've got those digits. And then divisible by 10 is actually a combination of the test for 5 and 2. So if you have a number that's divisible, that ends in either 0 or 5, and then also is in the list 0, 2, 4, 6, or 8, well, the intersection of those two would be 0. So divisible by 10 the ones digit is 0. How do you know if something's divisible by 100?
It'll be if there's 2 zeros at
Yeah.
place and 1 in the 10th place.
Absolutely. Divisible by 100. The last 2 digits are 0, 0. Okay. And, whoops, this should say by 100. My bad. If you had 1,000, then you would look for 3 zeros, and so on. So those are pretty easy to do. You can just inspect it, done. So like if for some strange reason I wanted to start a factor tree on 16,000, I could actually split that up as 16 times 1,000, because since this has got 3 zeros, so that means it's divisible by 1,000. And then take my factor tree from there. And that's a good way to start it, rather than starting with 2, which would take a lot more work actually than starting it here. Okay. Well, what other kind of test can I run? Anybody know the test for 3?
If the sum of all digits is divisible by 3.
Excellent. Yeah, if you add up all the digits in the number and that number is divisible by 3, then the number you started with is divisible by 3. So you add all digits. If the sum is divisible by 3, so is the original number. This one is really handy, and it really usually doesn't take too long to do this. A minute ago, I had this number, 12,486. We said it's divisible by 2 because it ends in 6. Well, now the question is it divisible by 3? Now, if you had a calculator, that's easy, right? You just plug it in there and you find out if it comes out evenly or not. But if you're doing this pencil and paper, I don't want to have to divide that whole thing out and find out it's not divisible by 3. So what I can do instead is I can add 1 plus 2 plus 4 plus 8 plus 6. And this isn't too hard to do in my head. Let's see. I've got 10 and then another 10, 21. If I'm adding right. Check my arithmetic if I'm not. 10. No, this should be 11, right? So 21. Do I get 21? 10, 1. Okay, is 21 divisible by 3? Well, yeah. We don't care about the 7, but you can divide that by 3. So what that means is 12,486 is divisible by 3. Because when you add those digits up, you get a number that's divisible by 3. Now, that also gives us another factor that we could use, because if it's divisible by 2 and it's divisible by 3, what's that mean in terms of another number that it would be divisible by?
6.
Yeah, if these are both factors of 12,486, then 6 also has to be a factor because, we're multiplying and dividing, so that has to be true. So if it's divisible by 3 and it's divisible by 2, that means it is divisible by 6. You can make up new rules for divisibility by using previous divisibility tests as long as the rules involve numbers that don't have a common factor. All right, so in this case, 2 and 3 don't have a common factor other than 1, obviously. 1's a factor for everything. And so we can combine those 2 rules to come up with the fact that if we wanted to, we could start a factor tree for 12,486 by using a 6. Okay, so far we've got a test for 2 and 3 and 4 and 5 and 6 and 8. I'm not going to talk about tests for 7. There are tests for 7, but quite frankly, they're not that useful in this day and age. If you're interested in divisibility tests, all you have to do is Google divisibility tests and you can find that out. We're going to focus on the ones that are most useful for us and our students today. And one of those is divisible by 9. So what's the test for divisible by 9? Well, it's similar to the test for 3, except now when you add up all the digits, they have to divide by 9 to be, for the whole number to be divisible by 9. So add all the digits. And if the sum is divisible by 9, and so is the original number. Oops, ran off the screen. Sorry about that. So just kind of going back up to this for a minute. When we added this up, notice we got 21. That told us this is divisible by 3, but not divisible by 9. So it's only got that one factor of 3. Well, what about, what if I had this number? $1,234,567,890. So is that divisible by 9? Let me show you a shortcut. You could add all those up like we said, but here's a shortcut for doing this. What I do is I find pairs of numbers that add up to be 9. So notice if I take the 1 and the 8, that's going to give me a 9. If I take the 2 and the 7, that'll give me a 9. The 3 and the 6 will give me a 9, and the 4 and the 5 will give me a 9. So what I've basically got is 9 plus 9 plus 9 plus 9 plus 9 plus 0. And if you can pair up all the digits and get 9s, you know, by taking everything into account, that means that this number is actually divisible by 9. Now, this can also help kids learn their 9s facts. I don't know if you guys ever thought about the multiples of 9. And maybe some of you learned this little thing with your hands. So I'm going to see if I can do my hand so it makes sense to you guys. So if you're going to do multiples of 9, you can stick your hands out in front of you, and let's say I want to take 9 times 4. So I'm going to go, let's see if this is going to work. 1, 2, 3, 4. Okay, so I get 36. Does that make sense? Let me make this bigger so that I've got somebody sitting in the room and I don't know if they can tell what I'm doing here. Okay, let's try this again. Okay, so if I'm doing 36, I go 1, 2, 3, 4. I'm sorry, if I'm doing 4 times 9, 1, 2, 3, 4. I put that 4th finger down, and that tells me I've got 30 and then 6. And so 3 plus 6 adds up to 9. If I'm going to do 9 times 7, 1, 2, 3, 4, 5, 6, 7. So I get 63. And so for some kids, that's helpful. My dad actually taught me this trick for 9, and I didn't do the finger thing, but basically he said if you're taking, say, 9 times 6, you take 1 away from the 6, that gives you 5, and then you figure out what you would add to 5 to get 9, which is 4, so 54. So I was the first kid in my class to actually learn all my 9s, because that seemed pretty easy to me, is to figure out how to do that using that little trick. You take 1 less than what you're multiplying by, add what you would need to get 9 for the 1's place, and done. So the divisibility by 9 is a handy trick to have. Now, how do we use this sometimes? Like I said, when you see this divided as plus, you might see some problems like this. So let's say we've got a set of digits here. So I'm going to go back to my share. All right, so let's say that we have 12,400 blank 2. Okay, and I think the book will put like a D here. So what if you wanted to replace D with a digit that would make this number divisible by 4? What digits could you replace? So what could D equal to be divisible by 4? Well, remember the rule was the last 2 digits, the 10 and the 1's digit, had to form a number that was divisible by 4. So what kind of replacements could we put in here for D that would make a number that's divisible by 4?
1.
1, because that'd give you 12. Okay, what else?
3.
Yeah, 3 more. It'd give you 32.
7.
7. Yeah. Did I miss one? So obviously 12 is divisible by 4. 32 is, yeah, 5. 52 is divisible by 4. And then 72 is divisible by 4. So you actually end up with 4 possible replacements for D that would make this number divisible by 4. And like I said, there's some problems like that. Let's do one more. What could D equal to be divisible by 3? All right, well, in this case, we have to add up 1 plus 2 plus 4 plus D plus 2. So let's see what that gives us. That gives us 3, 7, 8, 9 plus D. Oh, well, 9's divisible by 3. So what possibilities then could we add to 9 to still have a number that's divisible by 3? So D could equal what?
0.
It could be 0.
Or multiples of 3.
And yeah, another multiples of 3. So if we add 0 to that, that's going to give us 9. If we add 3 to that, that gives us 12. That's divisible by 3. If we add 6 to that, we still have something that's divisible by 3, right? That's 15. And if we add 9 to that, we get 18. So it looks like we have 4 possible replacements for the D, for this tens digit, so we end up with a number that's divisible by 3. Okay, so does that make sense? You've got a couple of examples of how to do those problems when you run across them in MyLabs Plus. Okay, well that basically should cover the gist for 4.1 and 4.2. 4.3 is over least common multiple, greatest common factor. And I'm going to hold off and do that next Wednesday during the regularly scheduled class because I know several people had to miss. And that LCM and GCF stuff is really, really, really important for fractions later. So I want to make sure more of the students are here to kind of catch that when we get back from the 4th of July break. So any questions anybody has at this point as to kind of what is going on in those first 4 sections? I know, Brittany, you'd have some questions, I think, about Chapter 4. Does that kind of answer most of your questions, or did you run across something else that I didn't talk about today?
I'm looking at the homework problems right now, so I can ask.
Anybody else? Now, the one thing I didn't talk about, which is in the notes, and I would suggest that you look at my online notes for Chapter 4 just to make sure that, you know, anything I might not have talked about directly you've picked up on. But there's something called the fundamental theorem of arithmetic. And all that says is that all of your natural numbers bigger than 1 are either prime or there's some kind of product of primes. And that means that when you get those prime factorizations, they're unique. They're not being shared with other yeah. So you're not going to have more than one combination of primes that'll work. You'll just have one combination that works for each number.
Number, I think it was 2 on the homework for 4.1. That was confusing to me.
Can you read it to me?
It said, suppose the product of 2 natural numbers is odd. A whole number is even if and only if there is a whole number k such that a equals 2 times k. A whole number b is odd if and only if there is a whole number j such that b equals 2 times j plus 1.
Okay.
And then it said, why must both factors be odd?
Okay. So
and then it had like 4 other questions with it.
Right. Let me go back to the share real quick. And that's getting into that number theory stuff. All right. So we're saying that the product of 2 numbers is odd. Is that correct, Brittany? I'm just calling the 2 numbers x and y.
Yes.
All right. So one of the things that makes a number even is if one of the factors you've got is 2. All right. So if you've got 2 times something, and they called it like J or K or L or something like that. I'll call it J here. So we know 2 times J is even because 2 is one of the factors, all right? And we can force something to be odd by adding 1 to that, because what that does is it jumps between the even numbers. So 2J plus 1 is odd. Okay, so if you've got two numbers that are multiplying together to give you an odd number, if one of them's even, let's say that this x was 2j, then there's really nothing you could do to y to end up with this 2j plus 1. I mean, it just won't happen. So the only way you can get an odd number is to have y, I'll call this 2k. Well, hang on a second. Let's let x be 2j plus 1, and then k or y will be 2k plus 1. So they're saying plus 1, there we go, that you have to have two odd numbers basically to get an odd number product. So think about foiling this out. If I foiled this little thing out, 2j times 2k would be 4jk. Well, because 4 is even, that means this term right here is an even term. And then you'd have 2j plus 1, or times 1, so you'd have 2j, and then you'd have 2k. So these terms, it's an even term, an even term, an even term, but then the 1 times 1 gives you 1, and that forces this then to be an odd because you've got an even plus an even plus an even. Those are all going to be evens, and then the 1 makes it odd. So it turns out that you have to have two odds to get an odd. There's no way to get an odd number by multiplying an even number times an odd number, because that even number is always going to have a factor of 2, and as soon as you introduce that factor of 2, you make the product even. It's just kind of the definition of even, is that 2 is one of the factors. Does that make sense, Brittany?
Yes, it does. I guess the way it was worded on the homework, I was just getting confused.
Yeah, it's worded because, I mean, again, that's sort of how number theory language looks. When you take a number theory course, everything's like that. Because you're trying to prove it for every possible case. So instead of giving you an example, they give you this, 2k plus 1 or 2k or whatever to describe all the possible even and all the possible odd numbers. So was there another number in that set, Brittany, that we needed to look at, or does that kind of help you figure out the rest of those in that set of questions?
I think that was fine.
Okay, well, if you run into something else, just send me an email. All right, anybody else come up with anything as they were looking at maybe the 4.1 or 4.2 material? All right, then. Have a great 4th of July. Make good choices. Do not come back with a finger missing. I'm going to do the same because I do like to blow stuff up. So I always have to be careful, too. We actually tried to blow up my outhouse one 4th of July. My cousin did. Cousin Jimmy always tries to blow stuff up. It was funny, but it's still standing. So anyway. So be careful out there. I will see you guys next Wednesday. And if you have any problems with either the weekend quiz or this stuff out of Chapter 4, just send me an email. I'll be checking my email, even though I'll be celebrating. We're actually celebrating tomorrow. My whole family's coming out, and we blow stuff up and play music and have a good time. So, but I'll try to check my email a couple times in the morning and then the afternoon tomorrow, and then I get to rest on Saturday and Sunday. So, anything else?
Just to clarify, the test on Friday the 8th is over chapters 3.4, 3.5, 4.1, 4.2, and 4.3?
That is correct.
Okay.
We will cover 4.3 next Wednesday and then do any review that we need to do then too. Okay? Have a good one. I'll talk to you guys later.